So in this video, we're focusing on linear independence in three-dimensional space R3. And this is an extension of the last couple of videos, but we've said that in order to span R2, in order to cover all of R2, we really need two vectors that are linearly independent, that are both in R2. And in order to span R3, in order to cover all of three-dimensional space, we need three vectors that are linearly independent of one another, that are all in R3. And of course, we can see the pattern here. This tells us that in order to span any space, Rn, we need n vectors. We need them to be linearly independent of one another, and we need them to lie in Rn space. We also said in the last video that in order to span R2, we needed two vectors. We can't have one vector because one vector alone doesn't give us enough information to span R2. In the same way, in order to span R3, we need three vectors. If we have two or fewer, we can't possibly span R3. In other words, one vector can only span a line, one-dimensional space, R1, it can't span R2, and two vectors can only span a plane. It can only span R2. R2 is a plane. It can't span R3. And then we said for linear independence that if we have more than the appropriate number of vectors, those vectors won't be linearly independent. So because we only need two vectors to span R2, if we're given three vectors in R2, we know that they will be linearly dependent. And because we need exactly three vectors to span R3, if we're given four vectors in R3, we know that they will be linearly dependent. In other words, if we have fewer than the appropriate amount of vectors, we won't be able to span the space. If we have more than the appropriate amount of vectors, then the vector set will be linearly dependent. So we just want to kind of clarify those points, but the main focus of this video is just to show you that in order to test for linear independence in 3 dimensions, we can use the same test that we used in 2 dimensions. So let's say that we're given a vector set in R3. They're 3-dimensional vectors, and let's say we have the vector 1, 1, 1. Let's say we have the vector 0, negative 3, 2. And maybe the vector here 1, 0, and 3. If we want to test to see whether these are linearly independent, we simply put them into a linear combination and set them equal to the 0 vector. So we would say c sub 1 times 1, 1, 1, the vector 1, 1, 1, plus c sub 2 times the vector 0, negative 3, 2, plus c sub 3 times the third vector 1, 0, 3, and we set that equal to the 3-dimensional 0 vector 0, 0, 0. And then in order to solve this, we could either pull out a system of linear equations like we did before, or since the system's starting to get a little bigger, we can solve this with a matrix. So instead of saying 1 times c sub 1 plus 0 times c sub 2 plus 1 times c sub 3 equals 0 for the first equation, and then working across the middle to get the second equation, and working across the bottom to get the third equation, instead, we can just put this into a matrix. So we'll set up one matrix where the first column is the first column vector, then we have the second column vector, the third column vector, and then we'll go ahead and augment that with the 0 vector. And we're just going to use Gauss-Jordan elimination to try to put this into reduced row echelon form. So in order to put this into reduced row echelon form, we can see that we already have a pivot in the upper left-hand corner, the 1, 1 position of this matrix, so we'll go ahead and leave that there. And then we can, for the second row, subtract out the first row. So the first row will stay the same, 1, 0, 1, and 0. And then for the second row, we'll subtract the first row from it. So we'll say 1 minus 1 is 0, negative 3 minus 0 is a negative 3, 0 minus 1 is a negative 1, and 0 minus 0 is 0. Then for the third row, we'll again subtract the first row from the third row. So we'll say 1 minus 1 is 0. These are the zeros that we wanted to get here because we're trying to zero out the first column. We'll say 2 minus 0 is 2, 3 minus 1 is 2, and 0 minus 0 is 0. So we have that augmented. Now we want to look for the pivot in the second row. And in order to do that, we can multiply through the second row by a negative 1/3. That'll turn this negative 3 into a positive 1. So the first row will stay the same, 1, 0, 1, and 0. And then the second row will multiply through by negative 1/3. So negative 1/3 times 0 is 0. Negative 1/3 times a negative 3 is a positive 1. Negative 1/3 times a negative 1 is a positive 1/3. And negative 1/3 times 0 is 0. Then here for the last row, we want to get a 0 entry here where the 2 is in the 3, 2 position. Because we're trying to zero out the rest of the second column, we've already got the 0 up here in the 1, 2 position. Now we need to zero out this 2. So in order to do that, from this new second row here, we'll subtract out 2 of this new second row. So we'll say 0 minus 2 times 0 is 0 minus 0, or 0. 2 minus 2 times 1 is 2 minus 2, or 0. 2 minus 2 times 1/3 is 2 minus 2/3, or 4/3. And 0 minus 2 times 0 is 0 minus 0, or 0. Next, we want to try to force a pivot entry here in the third row, which we can do by multiplying through this last row by 3/4, because that'll turn this 4/3 into a 1. So when we do that, we're going to get 1, 0, 1, 0. That'll stay the same. 0, 1, 1/3, and 0. And then across the bottom here, we're multiplying by 3/4. We'll still have 0, 0, and then 1 and 0. And then our final step is going to be to zero out the rest of the third column. So we'll do that first by subtracting the third row from the first row to replace the first row. So we'll say 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 1 is 0, and 0 minus 0 is 0. Then for the second row, we'll subtract out 1/3 times the third row, because if I take the third row times 1/3, right here where this 1 is, I'll get 1/3 times 1 is 1/3. And when I subtract that away from the second row, I'll get 1/3 minus 1/3 is 0, which is what I want. I'm trying to zero out this 1/3. We'll get 0 minus 1/3 times 0. That's still 0. 1 minus 1/3 times 0 is still 1 minus 0, or 1. 1/3 minus 1/3 times 1 is 1/3 minus 1/3, or 0. And then 0 minus 1/3 times 0 is 0 minus 0, or 0. And then the last row is still the 0, 0, 1, 0. And so what we can see is that we've managed to transform the matrix into its reduced row echelon form. And remember, these columns that we started with, if we go all the way back to the beginning, these column vectors here represented C sub 1, C sub 2, and C sub 3. And so if we come up here to just the simplified version of the matrix, we still have the same columns. We can pull the solution straight out of the matrix, and what this is telling us is that C sub 1 equals 0, C sub 2 equals 0, and C sub 3 equals 0. In other words, the only combination of C sub 1, 2, and 3 that make this equation right here true is the 0, 0, 0 combination. So C sub 1 has to be 0, C sub 2 has to be 0, and C sub 3 has to be 0 in order for us to get a linear combination that's going to equal the 0 vector. And if you remember from the last video, that proves to us that these three vectors that we started with right here are linearly independent vectors. If we are able to find some solution other than 0, 0, 0, any non-zero solution where any of these values, C sub 1 and or C sub 2 and or C sub 3 is not 0, if we're able to find any solution like that, then the vector set is linearly dependent. But if the only solution we can find is all zeros, then the vector set is linearly independent. So because these three vectors are linearly independent, because we have 3 of them, and because since they're 3-dimensional, they lie in R3, we could also say that these 3 vectors span R3.